Let's talk about classification models in machine learning and AI. So, classification is one of the most fundamental tasks in machine learning and artificial intelligence. It focuses on categorizing data into predefined classes or groups, from spam detection in emails to diagnosis in healthcare. Classification models are, I'll say, heart of countless AI application. So it documents, explores the concepts, techniques, models, or practical application of classification in machine learning. We will talk about in great detail. So let's start with the basics of classification. So classification is a supervised learning task where the goal is to predict categorical class labels of new instance based on past observation. This process involves learning from label training data and applying the learning patterns to unseen data. The primary purpose of classification is to make predictions or decisions based on the input data, such as categorizing email as spam or not spam. And however, they're like key components. If we talk like features, these are the attributes or variables that serve as input to the classification model. For example, in email spam classifier, feature might include the frequency of certain keywords or the length of the email. Then, if we talk about class label, these are the predefined categories or groups into which the data points are classified. For example, spam, not spam are the class labels in the email classification task. Then is decision boundary. This is a boundary in the feature space that separates different classes, for instance, into two-dimensional feature space. The decision boundary might be a straight line or a curve line that divides the space into regions corresponding to different classes. Then is classifier. It's an algorithm or model used to perform classification. Common classifiers include logistic regression, decision trees, neural networks. So, and then the type of classification problem. Let's start with the binary classification. This involves only two classes. For example, uh, like spam detection earlier we talked, not spam. In healthcare we can it's mentioned like diseases or no diseases. Then is like multi-class classification. It involves more than two classes. For example, include it includes categorizing news articles into categories such as sports, politics, or entertainment. And if we talk about multi-label classification, in this scenario, the instance can belong to multiple classes simultaneously. For example, a blog post can be tagged as technology, AI, innovation at all once. Then we talk about metrics for evaluating the classification models. So, first one is accuracy. Accuracy is the most straightforward metric, I will say, calculated as the ratio of correctly predicting the instances to the total number of instances. While accuracy is intuitive, it can be misleading in cases of imbalanced data where one class significantly outnumber the others. For example, if 95% of email are not spam, predicting not spam all email yields 95% of accuracy but fails as a spam detector. Then is precision, which measures the proportion of true positive predictions to the total positive predictions. For example, true positives plus false positive. So high precision indicates a low rate of false positives, which is a crucial in application like fraud detection. Then is recall, which is sensitivity. It measures the proportion of true positive predictions to the total actual positives. So high recall ensures the most actual positives are detected. Uh, it can be a very useful in the medical diagnosis as well. And then is F1 score, which is harmonic mean of precision and recall, providing a balance between two metrics. It is especially useful when there is uneven class distribution. And then is confusion matrix, which provides detailed breakdown of prediction results. For example, true positives, which correctly predicted positive instances, true negatives, which correctly predicted the negative instances, then is false positive, incorrectly predicted the positive instances. This is called type 1 error. Then false negative, which is type 2 error. And then is ROC curve and AUC. ROC is receiver operating characteristics curve plots, the true positive rate sensitivity against the false positivity rate. And the AUC is like area under curve, which quantifies the overall ability of the model to distinguish between the classes. AUC values ranges from zero point 0.5 random guessing to 1, which is perfect classification. Then is popular class classification. Uh, we start with logistic regression. The concept is logistic regression is a linear model that estimates the probability of binary outcome using the logistic functions. It is suitable for binary classification and tasks that can be extended to multi-class problems through methods like one versus rest, which is also called OVR. And the strength of this is like it's very simple, interpretable, and efficient for linear separable data. However, it has some weakness as well. So, assuming a linear relationship between the features and the log odds of the target class, which may not hold for the complex data. And if we talk about decision trees, decision trees can create a tree-like structure where each node represent a decision based on a feature, and each leaf represent a class label. The tree is built by recursively splitting the data based on feature values that maximize the information gain or minimize impurity. So, if we talk about strength of decision tree, it's very intuitive and interpretable, and model can non-linear relationships. And if we talk about weakness, it's prone to overfitting, especially with deep trees, and requires pruning to improve generalization. And SVM, which is support vector machines. It constructs a hyperplane in high dimensional space to separate classes. The objective is to maximize the margin between the hyperplane and the nearest data point from each class that are support vectors. And if we talk about strength, it's very effective in high dimensional spaces and robust to outliers. However, it has some weaknesses like computationally, it's very expensive for large data set and sensitive to the choice of kernel or hyperparameters. And if we talk about KNN, K nearest neighbor, so it's a non-parametric algorithm that design a class label based on the majority of class among k nearest neighbors of a data point in a feature space. And it's very simple and require no training phase. However, in terms of weakness, computationally, it's very intensive during prediction and very sensitive to the choice of k and the distance metrics. And then is naive Bayes. So it's based on Bayes' theorem. Naive Bayes assumes independence between features, which simplifies calculations, and it's very fast and efficient and performs well with categorical data and the text classification. However, the drawback is assumption of feature independence is offered unrealistic, which can limit its accuracy. And in the last is neural networks. So it's composed of layers of interconnected nodes, which are called neurons. Neural network learns representation by minimizing a loss function using back propagation. Uh, it's very capable of modeling complex non-linear relationships, and it's very suitable for the large data sets. But in terms of weakness, it requires substantial computational resource, which is prone to overfitting without regularization techniques. And uh, talking about advanced classification techniques, assemble methods, assemble methods. First one is like random forest. Uh, it assembles decision trees trained using bootstrapped subsets of data, combining their prediction for improved accuracy and robustness. Then is gradient boosting machine, that is also called GBM, which builds models iteratively, focusing on correcting errors made by previous models. Then is XBoost and Light GBM, which is advanced version of GBM, optimized for speed, scalability, widely used in competitions and real-world applications. And if we talk about handling imbalanced data sets, we start with the oversampling techniques like SMORT, which is synthetic minority oversampling technique, which generates synthetic samples for the minority class to balance the data set. Then is undersampling, which reduces the number of majority class samples to balance the data set. Then is class weighing. It assigns the higher weights to the majority class during the training, penalizing misclassification more heavily. And And if we talk about deep learning classification, first like CNN for images, so it's convolutional neural networks specialized for image data. CNN use convolutional layers to extract spatial features. And then RNN is recurrent neural networks designed for sequential data. So RNN capture temporal dependencies through recurrent connections. And moving forward, so application of feature engineering and selection. First, we have to understand the importance of feature engineering. Feature engineering transforms raw data into meaningful features that improve the model performance. It is often critical for achieving high accuracy in classification tasks. Uh, and then techniques for feature engineering can be scaling, normalization, encoding categorical data, polynomial feature, and feature selection methods where they're like filter methods, wrapper method, and embedded method. However, if we talk about applications, it can be used in healthcare, finance, or natural language processing, which can do sentiment analysis, spam detection, and in talking about image recognition, facial recognition, object detection, and also can be used in retail marketing uh, for it. And however, there are like certain challenges, like the current challenge they have, like uh, models perform well on minority class, but it's more like they are having complex data, so making advanced model like neural networks more understandable and in terms of scalability. And in future direction, integration with the explained AI, which is explainable AI, which is XAI. So that is like developing a models that are both accurate and interpretable. And then is federated learning, so which enables the classification across distributed data sources without compromising privacy. And in the end, transfer learning, which is leveraging pre-trained trained models for new tasks with limited data. And in the this is it. Thank you for watching. Likes and subscribe. Thank you. Bye.